So picking up where we left off yesterday. Yesterday we talked about the parent functions, all in preparation for transforming them. And we do the parent functions because they're the easiest of all the functions to grasp. So you're going to find that that is true as we work through today's lesson. So today's lesson is on horizontal and vertical shifts. And your objective, you will be able to identify and graph a parent function of a given function. Identify and perform the horizontal and vertical shifts that are indicated, and then describe the transformations in the correct order. Okay, so in the left-hand side of your notes, you write down the term transformation. And let's break it down into the word parts. So let's do a little grammar lesson, a little English here. Breaking that word down, what is the base word in transformation? Base word. I don't want prefix. I don't want suffix. I want base word. Form. Form. Right here, form. So I told you I was going to ask you questions, but I did want to know if you knew that. Okay, what is in math? What is a form? It's a shape. Okay, so in math, if we're going to perform a transformation, we're going to take the form, maybe it's a circle, maybe it's a square. In our situations, they're functions. And we are going to do what with them? What does trans mean? Change. So we're going to change the shape. Possibly. To transform something is to change it, right? What is the suffix ation? Does anybody know? To act out. It's the act of or the process of doing something. The process of doing. It's an action. So if I'm performing a transformation, I am going through the process of changing a shape. So we're going to be doing that today. All right, so when we're working with functions, for our purposes, we're going to do 4 different types of transformations. And they typically are vertical and horizontal. They won't really be rotations. If we're going to do a rotation, we'll just do a double reflection. We'll reflect horizontally, then we'll reflect vertically. Okay, so we're going to start with the first type, which is the translation. So there's that ation again, the act of translating. Okay, what is a translation? Well, a lot of times we'll call it a shift or a slide. So today we will be just sliding the parent function or shifting it to a new location. It just means relocate. That's all a shift is. It's a relocation. So that's one. Another one is the reflection. A reflection is just a mirror or a flip. Now we can flip vertically, we can flip horizontally, okay? But a reflection is a flip. Then we can dilate or perform a dilation. Now when your pupils dilate, what do? Dilation isn't a squeeze down. A dilation is a open, it's a stretch. So, well, sometimes you'll hear people say that you're going to dilate on a scale of 1/4, which means you're going to squeeze it down and make it smaller. But we call this a stretch. And stretches can happen vertically or stretches can happen horizontally. Okay, the other thing that we're going to do is do constrictions. Like a boa constrictor, what do? They squeeze things in. All of these things are happening horizontally. Another word for this is a compression. typically you'll hear about your dilations and constrictions more as stretches and compressions. So it's shifts and flips and stretches and compressions. And compressions go like this and like this. So recapping real quick, translations are shifts and slides. And so we're just sliding things left to right and up and down. Reflections are flips. And you know, we can flip vertically and make reflections. We can flip horizontally. That should be it down there. You're right. Got it. So those are the types of things that we're going to be doing with our parent functions. We're going to graph the parent function, and then we're going to transform it using the numbers that get added to the equation or the function. So we're going to start with colored pens. And up here at the top above the word vertex form of functions, I would like you in black pen or pencil to write just the base function. Y is equal to the function of x. This is any base function here. This would be considered like our parent function, the most basic form of that function. And then, here, what I want you to notice, probably you need to get closer over here because I'm not wearing my microphone. Probably you'll notice that in my next line, there's my y equals f of x, all in black. And then I did everything else in red. And we call this the vertex form of a function. If your function's written in that format, then you can perform transformations. You don't need to get out your table of values. You can just graph the parent function and slide it around and squeeze it and flip it and whatever you got to do. Okay? So, vertex form of functions. So, there is something that you have to be careful of. When you have multiple things to do, like translate and reflect and stretch and compress, you have to do it in a certain order. Just like when you do the order of operations, you work in the grouping symbols, then you do your exponents, then you multiply, divide, then you add, subtract, right? Same thing happens when you have a sequence of transformations. So these instructions, I actually changed them for tomorrow's notes, say that if you want to do this properly, you have to apply transformations in this order. You start with the parentheses. I would like to say that you start inside the grouping symbols. Parentheses being one set of grouping symbols. You might be under a square root. You might be inside a set of absolute values. We're talking about numbers that are grouped and they're separated from everything else. Okay? This, you're looking for your horizontal shift. That is the very first thing that you do before you reflect, before you stretch, anything. The first thing you do is shift your parent function left or right. Okay? After that, and today we won't be doing step 2, you're applying your multiplication. That's going to happen here, right? A times x, that's multiplication. That's going to tell you it's going to stretch vertically or it's going to compress vertically. Also, your other multiplication is right here, b times x. That's a horizontal stretch or compression. Okay, so that would be the second thing you do. After you do that, then you do your negations. This is when your A is negative or your B is negative. That's going to flip your graph upside down or left to right. My ear is ringing. Number 4, last thing is your addition and subtraction. That's your D term. That's when you push the graph up and down. Okay, so step 1, translate left to right. Step 4, translate up and down. And those are the only ones we are doing today. So have them by your side when you're working through these problems, these steps. Okay, so today's focus is the horizontal. And you know what, let's make sure that when you do this, you do horizontal before vertical. Keep it alphabetical. Keeps it organized. We always do the horizontal motions before the vertical. It's kind of like you always learn to crawl before you learn to stand up and walk, right? Babies always lay horizontal before they ever learn to stand up and get vertical. Okay, these are your translations or shifts. So we're not going to transform the shapes and make them look different, have really fat parabolas or really skinny parabolas. We're just going to take the parent function. It's going to look the same. They're going to be twins. They're just going to live in different houses. Okay, so we're going to identify the function family. That's a skill you have to be able to do. And you're going to graph the parent function, which is what your green paper is for. Then you're going to identify your horizontal shift. This is coming from your C term. And you're always doing the opposite of C. So if it says +3, you're going to shift left 3. If it says -2, you're going to shift right 2. Because what you're trying to do, remember, is to zero out that quantity, to figure out what's happening on your domain. After we do that, we're going to identify the vertical shift. This is your D term, and it's not the opposite of D. It's exactly D. If it says +3, we go up 3. If it says -2, we go down 2. Okay? Then using the shifts, you're going to graph the corresponding points on the given function. So we're just going to relocate the parent function. After we do that, I am going to ask you to describe the transformation in the correct order. We're going to do some examples so that you understand everything that we're putting in words. Okay, so colored markers, here we go. We're going to start with a horizontal shift example. Okay, and so I'm going to do this basic function here in black. So this is a function, y equals f of x. It doesn't have any numbers in it, and I'm just going to create one. So I'm just going to make a function up. It's not a parabola. It's not anything like that. I'm just going to graph a curve. So let's put zeros at -2 and 1. Excuse me. And a y-intercept of 1. Okay. So this is the top of some function that I'm graphing, but we can only see this part of it. And let's just connect it. Use your y-intercept as your peak. And then curve through it and come back down. And just put arrows on each side to indicate that that function continues to do whatever it's doing. Okay? So that's our basic function. Now we're going to take y equals f of x, and we're going to perform the horizontal shifts. And I do have a typo here on, we'll just do this one. Let's change it to a -2. Okay? I meant to do that. All right, so I'm going to graph this one in purple so that I can see what's happening. So what kind of shift am I going to perform on my y equals f of x? What am I doing with it? I'm pushing it to what zeros this out? -2? A regular 2, right? Because we're doing -2. So that means we're going to push the graph the opposite of -2, +2, to the right. So you take all of your points, take all the corresponding points here, and you're going to move them 2 to the right and replot them. And then just redraw your curve. And you have just performed a translation using this number. Your C term. Well, the opposite of C, right? The opposite of -2, +2. Let's do the other one. I'm going to do it in red here. You can choose your colors, of course. I hear somebody out here has one of those pens with you just click the different parts of it and it changes out the colors. Ooh, I need to get me one of those. Okay, so let's look at this. This is y is equal to the f of x plus 3. So what kind of shift is that? -3 or left 3. So all of the points from my original y equals f of x, because it's y equals f of x, are going to shift left 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And there you have examples of how that number affects the graph. Okay, let's do vertical examples. So vertical shifts on the back. Here we have the same set of, same kind of problem. I'm going to start with the one in the center. And I'm going to do this one in black ink. And I think I'll put a 0 at -3 and another 0 at +3. And then my y-intercept at -1. And we'll just do an absolute value one here that goes like that. Now, I'm not going to ask you to write the equation of this. We're just going to call this our base function. Okay? So here I have y equals f of x. 3 and -3, and then the y-intercept's at -1. If you get yours graphed in different points, that's fine. Maybe your graph looks different than mine. It doesn't matter. Just, oh yeah, I got you. Yeah. Okay, so let's go to the first one here. I'm going to graph this one in purple. You'll notice that these are identical. They're like identical twins here. They're both y equals f of x. There's no shift on the x. There's nothing to zero out the x but a 0. So this number that's out here as you're adding 2 means that you're going to push the graph up 2. And that's it. All the points are just moving up 2. And you regraph them. So just up 2. What are they watching next door? Again? Different version. This doesn't sound like the Walt Disney cartoon Alice in Wonderland. Is it the one with Johnny Depp? Oh, okay. For those of you watching the video, you're missing out on some loud noises. Okay. Those are just little arrows that I drew. Probably they look like points. I'm going to erase. Up 2. All right. Now I'm going to switch to red for my last one. Again, identical, except for this y equals f of x. If I zero that out, I get an output that says I need to push that graph down 3. Okay, so down 3. So taking this corresponding point here at your y-intercept -1 and push it down 3. Down 3. Down 3. And regraph. And you have performed a vertical translation. And I have forgotten to do a couple of things. Let's describe what's happening for these graphs. So I'm going to start with my red description right here. How did I get this red graph? Where did I start? Where did I start? Read the parent function, right? So for my red one, I'm going to say y equals f of x translated 3 units down. And I've meant to do this the whole time for every transformation that we have performed. I just am old and tired and I forget. Okay, so now that you have an example of that, how would we describe the transformation for our purple graph? This time I'm going to say slid. Wasn't that what I did? Didn't I just slide it up? Interchange your terminologies for your verbs. You should. Just, it'll get boring otherwise. Excuse me. Okay, let's go to a practice example now. And there are some specific instructions that we need to follow. Of course, I am going to let you change the color red to any color you want. I'm going to use red. It says, graph the parent function in dashed black and the G function in solid red. Again, you can use blue or purple, whatever color you want. Describe the transformation in the correct order. So here's where your skills have to come in to play. I'm not giving you the basic function. You have to identify it. So what family does the G function here, what family does it belong to? The quadratic. How do you know that? Because it's an x squared. So it belongs to the parent function, f of x equals base function. Most basic quadratic says x squared. Okay, so we have to be able to identify that it belongs to that family, and then you have to graph the parent function, which has a points at 0, 0, 1, 1, 4, 2, and then reflect those, of course. Dashed line here, because that's not really what we're supposed to be graphing. We're supposed to be graphing this other function. But anytime I can, of course, I'm going to graph the easiest graph that I can, and the parent function is the easiest graph. Now I'm going to go pick up my red pen, or you're going to pick up your other color, and we're going to look at our equation that's written in Vertex form. Look, our A is 1, our B is 1, our C is 3, and our D is -2. So we go for our horizontal shift. What's happening? We're going to be pushing this graph the opposite of 3. So we're going back 3, and then after we do that horizontal shift, which always happens once, we are going to push this graph down 2. So these are the transformations that we're going to apply. So starting at the origin, I'm shifting 1, 2, 3 left, down 1, 2, and replotting. And I'm doing the same thing with all of my points. Left 3, down 2. And of course, I'm just drawing these arrows. Please don't put them in your notes. Okay? 1, 2, 3, down 2. 1, 2, 3, down 2. Oh, no. 1, 2, 3, down 2. And then solid red or solid blue, whichever color you choose. You have now graphed the function that I assigned. See? It's nice. It's a good skill to have if the equation's written in vertex form. And take a look at that. The vertex is at -3, -2. I like it. Gives me a good starting point. Let's describe it. What did I do first? What did I graph first? The parent function. So I'm going to say f of x equals x squared was shifted. Which motion first? Okay, so I'm going to say horizontally. I'm just being fancy. Left 3. Of course, that's horizontal, right? And vertically, down 2. This is going to be a requirement today. Okay, so that's the end of today's notes. That's about as complicated as it gets. Make sure you do your